So I want to talk to you about statistics. Now, a lot of the time, statistics can be a pretty dry subject, right? It is fundamentally it's mathematics, and so that can be quite intimidating. And to make matters worse, I'm going to do some maths. I'm going to show you formulas and equations, right? However, almost none of these, basically just one of those, I'm actually going to expect you to remember. It's not even a complicated one. So don't worry, right? But we've got to go into this maths because I want you to kind of understand what statistical tests are actually doing. So let's start with a motivating example, right? So the Meyer-Overton correlation is a pretty famous correlation in pharmacology, how drugs work. What it says is that the more lipophilic a drug is, the more easily an anesthetic dissolves in fat, how far to the right they are on this graph, the more potent that anesthetic is, right? So you have chloroform, which is very fat soluble, along with halothane, and they need a very low concentration to put you under, while xenon is much less fat soluble, and you need a much higher concentration to put you under. Now, this correlation was shown over 100 years ago, and it found like it was the formative idea in how anesthetics worked. Basically, they must dissolve in fats because of this correlation. Turns out that was actually wrong. We're not going to go into it, as I say down there. This is not what we're. I'm not going to be testing you on, right? The point here is that we have this correlation, this linear relationship. But let's go back to the original paper by Meyer. It's in German. It was not much fun for me to try and pull the original numbers out. This is the original numbers that he published first of all. And as I say there, they're not really as convincing as that first graph. In fact, should you believe that that correlation exists at all? Does that relationship exist there? And it kind of looks like it does, right? That, the one that's the most oil soluble over here to the right is the most potent. But I don't know, right? And that's the point of statistical tests, basically, is to change our, is to basically put in data and get an answer out. Now, there'd be lots of statisticians who'd get very upset by me saying that, right? But fundamentally, that's how they are used in biomedical research. We put in our numbers, we get out an answer, and we just say good enough, right? And that there is why I think it's so important that you actually understand what is going on in these hypothesis tests, right? And we're going to talk about what that really means. So linear regression is I would argue, even though probably most people wouldn't, is the simplest form of statistical test, right? And it basically asks this question: if we fit a straight line to our data, is the slope of that line statistically different from zero? Right now, what does statistically different from zero mean? How can we know if a slope is statistically different, right? We'll get into that. But before we get into that, I want to talk about R squared, right? R squared is something that probably most people are not most people, probably most people are not aware of it, but most people who've ever played with a graph, Excel, tried to understand numbers is sort of vaguely aware of. And if I probably asked most people what R squared was, most people who knew what R squared was, they'd say, oh, it's sort of how close the data reaches the line, right? I want you to think about R squared as being the explained variation divided by the total variation. What does that mean? All right, it's not super scary. All right, here's this original data again. This maroon line is the mean of all of the data on the y-axis, right? So it's the mean of their anesthetic threshold. And the total variance is just how much this data varies from this line, right? How variable is this data? How do we calculate that, right? It's an equation, but it's not really that bad. We take each data point, yi, the y value for the ith data point, the first, the second, the third, the fourth. We subtract the mean from it. We get some number. We square it, and then we sum all of these data points up. Why do we square it? Well, because some of these distances from the mean, some of the yi's minus mu's, which is just the length of that line, some of them will be positive, some of them will be negative. So if we added them all up, they would tend towards 0. However, if we square them before we sum them all up, the positive ones stay positive. Any positive number squared is another positive number. And the negative ones go positive. Any negative number squared is a positive number. So we add them up and then we divide them by n, and that gives us the average distance squared from the line. It's our measure of total variance. So that gives us our total variance. But what about this variation explained? What does that mean? Well, we can't actually calculate it directly, but what we can calculate is the unexplained variance. And we work on the assumption that total variance must equal the sum of the explained variance and the unexplained variance, right? Because all variance must be either explained or unexplained, right? All animals are either cats or not cats. So can we calculate the total variance and the unexplained variance? Yes, we can. See, this here, the length of these black lines is the unexplained variance, because this is how far the data is from our prediction, this black line, the line of best fit, right? So the equation looks almost the same, except instead of it being the distance from the mean, we now calculate the distance from the line. So this is our unexplained variance. So I said R squared is explained variance divided by total variance. We calculate explained variance by doing total variance minus unexplained variance. These are just numbers that we just calculate. As I saw, it's the average squared length of those lines. We just do the maths and we come up with R squared is 15%, or 15, or 0.15. So that's not a very good fit. Okay. I just want to sort of put out to the side, right, that when we did this equation, we got our variances by summing up the squared distance between either the mean or our line of best fit, and then dividing it by n. But n in both of these cases was the same, and so they just cancel out. So actually, we don't even need to divide each one by n. And so we can just calculate the sum of squares. Statisticians love the phrase sum of squares, and it's just the variance, but not divided by n, right? So when you hear sum of squares, you should just think variance. It depends which sum of squares it is. Is it the total sum of squares, or the residual sum of squares, which is another word for the unexplained variation, because those lines, those distances between the data and our best fit is called the residual. Sort of it's what's left over from the best fit. So point being, sum of squares is just a shorthand for variance.